D-Wave use cases for quantum annealing computers. Executive summary. Quantum annealing uses quantum effects to solve complex optimization problems expressed as QUBO or Ising models. D-Wave systems address large real-world tasks in finance, machine learning, simulation, sampling, and constraint satisfaction, since many non-optimization problems can be mapped to optimization form. Case studies show practical value: Volkswagen traffic routing, save-on-food scheduling, Denso manufacturing, protein design and folding, anomaly detection, retail inventory planning, grid optimization, and portfolio construction. These applications demonstrate commercially meaningful performance. Article D-Wave makes quantum computers that use annealing to solve some classes of optimization problems. Millions of businesses have these problems. I think D-Wave will make money solving these problems. There are other problems that annealing quantum computers can be used for. Their native strength is solving optimization problems, yet many other tasks can be mapped onto optimization formulations, allowing quantum annealers to tackle a wider range of problems than you might expect. Quantum annealing is a quantum computing method used to find the optimal solution to complex optimization problems by leveraging quantum mechanics, such as superposition and tunneling. It works by exploring a solution space to identify the lowest energy state, which corresponds to the best solution for the problem at hand. What quantum annealing is naturally built for. Quantum annealers, like those from D-Wave, are designed to minimize an objective function, usually expressed as QUBO, quadratic unconstrained binary optimization, or Ising models. Quadratic unconstrained binary optimization, QUBO, is a type of combinatorial optimization problem where the goal is to find the best binary vector that minimizes or maximizes a quadratic function defined by a matrix. That's above my pay grade, but suffice to say these are real problems, and D-Wave has a real solution for some of them. Quantum annealing has applications in various fields, including finance, machine learning, and quantum computing, and is known to be NP-hard, meaning it can be very challenging to solve efficiently. These frameworks describe a huge number of computational tasks, not only optimization. Non-optimization tasks that can be mapped for quantum annealing. 1. Machine learning. Many ML tasks can be rewritten as QUBO problems, allowing quantum annealing to be used for clustering, feature selection, training Boltzmann machines/RBMS, sampling tasks. This is particularly promising. Annealers do fast approximate sampling. Quantum annealing isn't replacing GPUs, but it offers alternative approaches for ML tasks with combinatorial structure. 2. Sampling and Boltzmann sampling. Quantum annealers naturally generate samples from low-energy distributions, useful for probabilistic inference, approximate Bayesian computation, generative models. This is not strictly optimization. It's closer to statistical physics simulation. 3. Simulation of physical systems. Annealers implement Ising models directly, so they can simulate magnetic systems, spin glasses, certain quantum materials, via effective models. This is analogous to analog quantum simulation. 4. Graph problems beyond optimization. Even non-optimality questions can be encoded. Graph coloring, subgraph detection, satisfiability checks, constraint satisfaction, CSPS. They become yes/no feasibility problems expressed through energy penalties. 5. Error, correction and code decoding. Minimum weight perfect, matching for decoding quantum error. Correction codes can be tackled using an annealer. This is actually an important research direction for fault-tolerant quantum computing. 6. Cryptography, limited cases. Not breaking RSA, but some cryptographic primitives involve lattice-based problems, icing-style encodings. Some hard instances can be mapped to QUBO to explore hardness assumptions, tasks annealers are not good at. These cannot be done efficiently with quantum annealing Shor-type algorithms, factorization, discrete log, Grover-style unstructured search speedups, general quantum circuit/universal quantum computation, simulation of arbitrary quantum dynamics. Quantum annealing is not a circuit model quantum computer. Summary. Quantum annealing is primarily an optimizer, but optimization is broad enough that many non-optimization problems can be encoded into it. Quantum annealers can effectively handle sampling, machine learning tasks, physical simulations, constraint satisfaction, error correction decoding, certain graph and feasibility problems. So yes, they are more versatile than they appear. You can go deeper using the link in the blog. Topics suggested by GPT, specific industry case studies, example QUBO formulations, how to run an optimization on D-Wave using Ocean, Python, comparison with gate model quantum computers, case studies. Here are clear, real public case studies showing how organizations have used D-Wave quantum annealing and hybrid solvers in production or advanced prototypes. These are verified examples from D-Wave's published materials, partners, and customer announcements. 1. Volkswagen, traffic flow optimization, Beijing and Lisbon. Problem: optimize taxi routes to reduce urban congestion. Approach: mapped real-time traffic data to a QUBO, solved with D-Wave's quantum annealer. Results: optimized routes for thousands of taxis. Demonstrated at Web Summit in Lisbon with a live fleet. Reduced overall traffic load by smoothing flow across city segments. Key takeaway: quantum annealing worked on real-world routing problems with live data streams. 2. Save on foods. Employee scheduling optimization. Problem: large-scale grocery chain needed optimal staffing across hundreds of stores with changing constraints, roles, labor laws, budgets. Approach: hybrid solver solved complex shift scheduling, QUBOS. Results: reduced scheduling time from hours to minutes. Higher quality schedules than classical heuristics. Improve staffing efficiency and customer service. Key takeaway: real, commercial use of quantum hybrid scheduling executed at scale. 3. Denso, factory robot and process optimization. Problem: factory layout and workflow timing for multiple robotic arms with collision and throughput constraints. Approach: converted optimization constraints into QUBO, solved with hybrid quantum solver. Results: improved layout and path timing, reduced cycle times, increased overall throughput. Key takeaway: industrial manufacturing optimization is one of the strongest fits for quantum annealing. 4. Sinica, European HPC Center. Protein folding. Problem: predict low-energy configurations of proteins using lattice models. Approach: icing/QUBO formulations solved using D-Wave Advantage. Results: accurately reproduced known secondary structures. Demonstrated scaling advantages compared to classical heuristics for certain instances. Key takeaway: quantum annealing matches the physics of protein folding energy landscapes naturally. 5. Menton AI. Protein design. Problem: optimize peptide structures for therapeutic proteins. Approach: hybrid quantum classical system to find low-energy molecular conformations. Results: designed peptides that were validated in wet lab experiments. Reduced iteration cycles. Key takeaway: real biological discoveries assisted by quantum annealing. 6. Los Alamos National Lab. Machine learning, anomaly detection. Problem: identify anomalous patterns in data streams. Approach: trained quantum-boosted machine learning models using Ising-based optimization. Results: high-quality anomaly detection with competitive performance. Quantum annealing used to optimize model parameters. Key takeaway: quantum annealing is useful as a machine learning optimizer kernelizer. 7. Accenture plus D-Wave. Retail inventory optimization. Problem: finding optimal inventory levels across multi-store chains with supply and demand variability. Approach: hybrid quantum optimization. Results: reduced inventory holding cost. Better risk-adjusted stocking. Key takeaway: quantum annealing supports enterprise-scale supply chain planning. 8. GrooveKnots plus Japanese power utilities. Grid optimization. Problem: balance load and generation, wind/hydro/thermal, in real time. Approach: quantum annealing used to optimize power dispatch and stabilize renewable energy integration. Results: reduced peak load deviation. More stable integration of unpredictable renewable sources. Key takeaway: good match for energy grid scheduling problems. 9. Multiverse computing. Finance portfolio optimization. Problem: construct portfolios under return, variance, liquidity, and regulatory constraints. Approach: QUBO formulations plus D-Wave hybrid solver. Results: competitive or improved results versus classical heuristics. Works for large constraint sets where classical solvers push limits. Key takeaway: finance remains one of the most commercially promising domains.